The magnetic force on a charged particle is always perpendicular to the velocity. So, for example, if we have a positive charge moving in this direction, the force is going to be perpendicular to that velocity. Perhaps it's going down. So perhaps this is the magnetic force in this case. So the question is, how is the particle going to respond? Well, we actually talked about this back in Physics 1. When the force is perpendicular to the velocity, that's going to result in circular motion. And so what we're actually going to get is circular motion. And it doesn't matter where we're talking about. For example, if the particle's over here, that's the velocity. The force is going to be perpendicular to the velocity in that situation. And it's always going to point to the center. So I want to remind you of some of the terminology that we use with regards to circular motion. First of all, there's tangential acceleration. This is the acceleration due to speeding up or slowing down. This is how we calculate it. It's the magnitude of the rate of change of the speed. Okay. There is radial acceleration. This is the acceleration due to turning. It's the speed squared divided by the radius of the circular motion, so that would be right here. Okay. And we can also talk about the net force. Now we know from Newton's second law that the net force has to be mass times acceleration. If we're in a situation where we only have a radial force, that means we only have a radial acceleration, and so consequently, that means we can write this as mv squared over r. The other thing that I want to mention here that applies is work. Okay? And remember that work is the amount of energy transferred or transformed by a force. And we can talk about the net work. That's just the change in kinetic energy. We could also talk about the work done by an individual force. That's the force times the distance over which the force was applied, and times the cosine of theta. This theta, that's the angle between the force and the velocity. And I want to stress that in this formula, this force, it could be an individual force, such as the normal force, okay? Or it could be the net force. It could be either one. And this is the distance over which the object travels while the force is being applied. Okay, now let's talk about torque. Okay. So just to remind you of the formula for torque, the torque is the lever times the force times the sine of theta. Now the lever, that's the angle between, the distance between the rotational axis and where the force is applied. And theta here, this is the angle between the force and the lever. So let's look at an example. Let's say I've got this bar, it's set up to rotate about that rotational axis, and I'm going to apply a force right here, and the angle between the force and the horizontal there is theta. In this situation, the lever, that's the distance from the rotational axis to where the force is being applied. The lever is horizontal. All right, so this is horizontal. So theta is the angle between the force and the lever. And I should label the force there. So the lever is horizontal. Theta is the angle between the force and the lever. And that's all there is to it. Now in this case, the force is going to make this rotate counterclockwise. Okay. And before we may have just said that it was a counterclockwise torque. And I'm going to show this in another video. There's a right-hand rule we can use, but essentially it comes down to this. If we have a counterclockwise torque, what we used to call a counterclockwise torque, we would now say its direction was out of the screen or out of the page. And if it's a clockwise torque, that's going to be into the page or into the screen. And I'm going to show how that comes about. I'm going to show the right-hand rule for that in the next video, which is going to look at the second half of this problem, the diagram specifically, and it's going to talk about how to get that.